All right, so let's just keep going from where we left off last time. We're still doing the review part of the course. But that won't take too much longer. Probably by the end of the session, or maybe we'll in the middle of the next one, we'll start the brand new material. Something to look forward to. But right now, we can continue to review these first four sections of the preliminary or preview notes. So, where do we leave off? We started to look at what were called rational functions, and the word rational simply means ratio. Okay, so if you remember, we last time defined the concept of a polynomial. So basically, what's happening here is that anytime you have a ratio of two polynomials, we refer to it as a rational function. And of course, the one thing we must make sure is that the denominator does not equal zero. All right, now they're going to also throw some other terminology at us. So polynomial functions, which we've been talking about at great length, rational functions are algebraic functions. And informally, an algebraic function is one that can be expressed as a finite number of sums, differences, multiples, quotients, and radicals involving x to the n power. Okay, so it's a very general expression or definition rather, but some functions are not algebraic at all. And in fact, one of the classic examples of that is our trig functions, which we'll be studying in more detail later on. And you might remember, for example, if you want to see a graph of, let's say, the sine of x, we can go to our friend Symbol Lab and take a look at it. Here we go. And you'll notice it has some very strange properties compared to what we're used to seeing. Specifically, it just keeps going up and down and up and down and up and down forever. It's an infinite series of cycles, and it's just like a roller coaster essentially that never stops. Okay, so this is not an algebraic function. We call it a transcendental function. Now, here, what we're going to see here is that we can certainly combine functions in the way that we combine constants. We can add them, we can subtract them, we can multiply them, and we can divide them. So there's nothing really mysterious here. What is a little bit more involved is this notion of composite functions. All right, so what is that all about? All right, hold on one second. Here we go. So a composite function is a function of another function. I mean, that's basically all that it is. Okay. So how is that written? There's a few different ways we can write this. We can write f of g of x. We can write f. Now, this little circle here is used to represent a composite function. And then sometimes we write it like this. And you should just be aware they all mean the same thing. So here's the big question. How do we solve for a composite function? How do we figure out what that function is? Okay, so here's how it works. Suppose we have, um, and okay, well, here's a graph that'll help us understand the relationship between the domains and the ranges. What they're trying to tell us here is this. Um, the domain of G is X. The domain of F is G of X. When we bring them together, um, we end up with a domain of the composite function. But we'll see. This will make a lot more sense when we do some specific examples. Let's hang on to this for a bit. For now, what we'd like to do is actually show how to find a composite function. So here's an example. F of x equals 2x minus 3. And g of x is x squared plus 1. So we'll start with f of g of x. Okay. Now, I would like, before we do this, I just want to point out that if I was asking you to solve for, let's say, just this is just a side note, just to help make what's about to happen make more sense. F of 2 would be found by simply replacing all the x's in f with a 2. And so f of g of x is interpreted in a similar way. Each x in f of x is being replaced with g of x. So that's really all you're doing. You're saying, well, here's f of x. Every x is now being replaced with g of x. Now, we're not done, of course. We need to now substitute the actual definition of g of x. So this can then be written as, okay. And if you want, you can expand it out. It depends. Now, if you're doing this, let's say, as a web assigned problem, they might ask you to do this. So that's how that works. Now, we can do this in the other direction. We can also find g of f of x in the same way. So let me just copy these down here and we'll see how that works. Okay, so that means g of f of x equals, remember, g of x is x squared plus 1. So you're replacing all the x's in g of x with f of x. Now, of course, we will also now substitute the actual definition of f of x. And then, you might be able to just leave it like this. If you want, you could expand it out, but this is how you find g of f of x. Okay. Now, it turns out, interestingly enough, we can also define f of x. That's right. You can do that too. So let's see how that would work. So that means that f of x would equal 2 f of x minus 3, or x minus 6 minus 3, and that would leave us with 4x minus 9. And of course, if we can do f of x, there's nothing to stop us from doing g of x. So remember, g of x is x squared plus 1. Actually, let me fix this real fast. So therefore, g of x must be, okay, so it's g of x squared. Actually, let me write it like this. No, this is fine. All right, let's leave it like this. Okay, so in other words, the x squared became g of x squared plus 1, which is x squared. Oh, wait a minute. No, no. I forgot there's an extra 1 in there. Let me fix this real fast. I just realized I goofed. Let's try that one more time. That's better. Okay. All right, now we're good. Okay, that's much more like it. Okay, so g of x would have to be, since it's x squared plus 1, that's going to be g of x squared plus 1, and g of x itself is x squared plus 1. So this is what we're going to wind up with. Okay, now, as if that weren't enough, you also can have more than two functions combined together. You can define, for example, f of x, and then you could have, for example, f of g of f of x. G of, let's say, g of f of x. Anything goes with composite functions. Okay. But normally we don't need to go quite that far. All right. Um, okay. So I think that's all we needed to say about composite functions for the time being. Now, zeros of a function is the word zero here means the same thing as a solution. Okay. So in other words, let's say our function is y equals x squared minus 4. We clearly control this with a parabola. And what are we looking for? The 2 points where the parabola crosses the horizontal axis. Those are my zeros or solutions. And so how do we find them? Well, we set the function equal to 0. In this case, we'll have two solutions because it's a quadratic equation, but it's a particularly simple one. So we end up with x squared equals 4. And we end up ultimately with x equals plus or minus 2. So in other words, on this graph, you've got the 2 points, negative 2, 0, and 2, 0. And those are my solutions, okay? Um, or zeros, okay? Oh, and that's all they had to say about that. Okay, just a quick reminder. I guess they want to re make sure that you've forgotten all these haven't forgotten all these key concepts. Even in odd functions, this has to do with the symmetry of the graph. Um, so even, what does it mean to be even? Symmetrical with respect to the vertical axis is an even function. Okay, and so that would be, um, we can prove it if this is true for all x in the domain. So we had a bunch of these examples the last time we met. And so the classic example of this would be y equals x squared. For every x, we have the corresponding negative xy. Okay. So this is said to be an even function. It's symmetrical around the vertical axis, but it's also said to be an even function. And then an odd function, that's the one that's symmetrical with respect to the origin. All right. So the example I gave last time of this was this one, which means that f of x equals negative f of negative x. So that which is basically means for every xy we have down here somewhere the corresponding negative x, negative y. Okay. Okay. So it's really just terminology. Most functions don't fall into either category, or many functions don't fall into either category. Um, oh, okay. So here they want us to prove whether or not this function is odd, even, or neither. So well, this is what it looks like. And you can see that it clearly is symmetrical with respect to the origin, but we can prove it algebraically by doing the following. X cubed minus x. So what we're trying to do is show this. What happens if I solve for f of negative x? But if you notice, in turn, this is equal to negative f of x because you're just multiplying f of x by negative 1. And so that's all we need to demonstrate that f of x is odd and therefore symmetrical with respect to the origin. Okay. What else did they want us to do? They went ahead and solved for the 3 points, the three zeros. Um, they set it equal to zero. As you can see, they factored out x squared minus 1. And you can see there are three zeros where the curve crosses the horizontal axis. They are 0, 1, and negative 1. Now, this one is, well, I guess they've already let the cat out of the bag. It's even. G of x is 1 over x squared. So remember, even means f of x equals f of negative x. So let's prove it. And so these are equal to each other, and we're all set. Now, what does this thing look like? Ah, now that's an interesting one. So you can see what's on the right-hand side of the axis and the left-hand side, if the graph is drawn correctly, are mirror images of each other. So symmetrical with respect to the vertical axis. Okay, what else do we have here? Oh, this is what they have is first here is a case where it turns out to be neither odd nor even. Okay, but what's interesting about this one is that it doesn't have any real zeros because if you can see this graph here, it doesn't actually cross the horizontal axis at all. Oh, now that's kind of a problem because remember, zero means where does the curve cross the horizontal axis? So therefore, what this actually means is that this function, not only is it neither even nor odd, but it has no real zeros. Well, it turns out, as we'll see later on, it does have zeros, but they're imaginary. Okay. If you see a curve that doesn't cross, it means it has imaginary solutions. That can wait till another day, though. All right. Um, all right. So, they have these little practice problems at the end of the chapters. You can work on these if you need some practice. Like, for example, with this one, they're asking us to solve it for t minus 6. All right. So, in other words, all the x's are being replaced with t minus 6. Now, t minus 6 squared, for something like this simple, you can use FOIL if you want. T squared minus 6t, again minus 6t, and positive 36. We end up with t squared minus 12t plus 36. Now that all gets multiplied by t minus 4. Now this one can't be done with FOIL because the first expression has three terms in it. Now this is where it gets interesting. I think a lot of people have been shown how to do this in different ways. And it looks like the way I was taught to do this is may not be the way you were taught. When you have something like this, you're multiplying two polynomials. Um, you line them up and you basically go through them one at a time. That's minus 48t. And then this one would be 4t squared. And then you do the same thing for the t. 36t minus 12t squared t cubed. Make sure you line them up. Make sure you indicate which ones are negative, and now you add them. Now, other people have shown me like box diagrams and things like that that they've been exposed to. That isn't what I was taught to do when I was young. So this is what I know how to do. So I'll stick with this approach. But the bottom line is all you're really doing is making sure that you're multiplying each term in each expression, and you're not leaving anything out. That's really what you're doing here. So the final answer should be t cubed minus at squared. Something what went wrong. Oh, you know what I did? Did I copy something wrong? No, they got something else. Hmm. All right, let's see what happened. See, now in a mind tap situation, you'd get the wrong answer and you'd say, what happened? You go back and double check. So I didn't substitute anything wrong. This is fine. T minus 6 squared is indeed t squared minus 12t plus 36. Huh. Oh, I know what I did wrong. When I came across here, this is minus 4 and this is minus 12. This should have been plus. Uh, all right. I'll give them that. It is, yes, it was incorrect. It should have been 84. Those arrows, they made it hard for me to see, but the negative is way over here. That was not a good idea. So this is plus 84. Now we're good. And what was the other one they gave us? Oh, just domain and range. All right. This is the square root of x minus 10. All right. So that's what it looks like. Now you can see very clearly that x cannot be anything less than 10. It can be 10, but it can't fall below 10 because otherwise we end up with the square root of a negative number. So the domain is everything from 10 up to infinity, including the 10. So therefore, we use the square brackets. The range, on the other hand, refers to the y values that can be produced here. And you can see the range is only the non-negative numbers. It can be 0. If I plug in 10 here, I'll get a 0. But after that, everything will be positive. So the correct answer is D. Yes. Okay, wonderful. All right. So there's one more section here of our review. This was P3, it's called. Now we're going to move on to P4. Ah, review of trig functions. All right. By the way, I do want to point out that your calculators are capable of being very helpful with our discussion about trig functions. So I think it's mentioned in the syllabus that for a class like this, you should probably think about getting a really good calculator. I like the TI-84. Now, suppose you don't have one. Under normal circumstances, in a real classroom setting, I would insist that everyone has a real physical calculator. But since we're online anyway, it turns out you can get an app for that on your phone. And it's called, let me just make sure I've got the correct name. Calculate 84. The Calculate 84 is exactly the same thing as the physical calculator. Very, very occasionally there are subtle differences, but they're basically the same thing. So this has all the trig functions you could possibly ask for, which is why I'm mentioning it now. So, all right, anyway, let's see what they want us to do. So they start by reminding us what exactly an angle means in the first place. So what we have to do is visualize that two rays are being joined at one point. So if you remember from your probably middle school geometry days, a line goes both directions forever, but a ray has a specific starting point. All right. So if we bring these together, they come together at a specific point, which is known as a vertex. And we also assume that we know what direction we're going in. We're starting here. And this is the terminal ray, or sometimes it's called the terminal side. And then the distance that we have to travel can be thought of as our angle. And when we say distance, we mean relative to going completely around a circle. And if you remember, a circle contains 360 degrees or 2 pi radians. So if this theta over here on the left, by the way, that's the Greek letter theta. We always see it used to represent angles. If this represents 1/6 of a circle, for example, then clearly it must be 60 degrees. Okay. Now, normally, when we analyze angles, we're doing it with respect to the horizontal axis. We're assuming that we start on the horizontal axis. We don't have to, but it's just easier that way. So we call that the standard position. Yeah, it makes things so much simpler. Now, don't forget, as far as these quadrants are concerned, since the total circle has 360 degrees each quadrant, is 90 degrees. So, like here, this is meant to indicate we go all the way through the first quadrant, and let's say halfway into the second quadrant. So, therefore, the angle between these two rays is 135 degrees. That's how it's done. Okay. By the way, I just want to remind you, this will come up later on anyway. If you notice, we're moving in a counterclockwise direction. What if we're not? What if we're trying to come around from this side? Ooh, okay. Now that's going to change everything. Even though we wind up at the same terminal side or terminal ray, the angle is defined a little differently. When moving, in a clockwise direction. The angle is defined to be negative. Now, if you notice, by going in that direction, we went 90 degrees to get through the fourth quadrant, 90 to get to the third, and 45 more degrees to get through the halfway through the second quadrant. So we say that the negative version of this angle is 225. So basically, what this is showing you here is that they're both the same angle. Positive 135, negative 225 are what we call coterminal angles. Basically, that just means they bring us to the same end final point. Okay. So if we go counterclockwise, that's a positive angle, which is what we're used to, but it's possible to have a negative angle too. So we just have to remind ourselves how that works. Okay. Now, there's also some classifications here that are going to remind us an angle, if the angle is between 0 and 90, well, first, 90 degrees is a right angle. 0 to 90 is defined as acute. And of course, then 90 to 180 is obtuse. Yeah, once upon a time, you studied all of this stuff. I don't know what grade you were in, but you definitely have encountered this before. And then, here we go. So they're mentioning the negative angles. So here's their example. They went into the fourth quadrant. So we go, here's 90, 90, 90, 45. That's 315. But if we go in the opposite direction, the negative direction, you can see we're only going halfway into the fourth quadrant. And so negative 45 and positive 315 are coterminal angles. Now, I'm going to give you a helpful hint to help you remember how this works. Okay. Because, you might say, well, I don't want to have to draw this graph every time. If you're not sure, here's a helpful hint. If two angles are coterminal, then the absolute values or the sum of their absolute values will be 360. And that's the case here. Okay. In other words, um, and that's how you know without looking at the graph that they must be coterminal. Okay. All right. Um, Now, also, what can happen sometimes is what if you go around the circle more than once? Let's say we go around the circle, the normal way, counterclockwise, and then we go another 45 degrees. Well, you traveled 360 degrees to get around the circle and then another 45. So that means that these angles, 45 and 405, are coterminal. They both bring us to the same point. And of course, you can go around twice or three, as many times as you want. Now, radians, um, in my opinion, the best way to remember how to convert back and forth is to remember this one simple statement. If you remember that, you'll never have a problem. So, for example, so what I'm going to do is multiply that by pi over 180 degrees, and that's going to give me 4/3 pi radians. But if I want to go the other direction, then it becomes um, 270 degrees. So that's how you go back and forth between them. Now, on your calculator, when we get to a later chapter, when we start doing a lot of examples with trig functions, I'll show you that on your calculator, you can actually change the mode, switch it back and forth between degrees and radians. And so that way it can do a lot of this for you. Okay. And then the basic trig functions, I think we already started to do this the other day. Um, Sine, opposite over hypotenuse, cosine, adjacent over hypotenuse. Now, all of these, the rest of them are functions of sines and cosines. Okay, I just want to point out that the sine, and sometimes it's more helpful to treat it this way. Whoops, sorry, that's not right. It's O over A. But if you look at it carefully, that means that the tangent is the ratio of the sine over the cosine. Look at that. Because we have O over H over A over H. Oh, yeah. So you're going to see as we go along, there's a lot of trig identities. And so often what we end up doing is we use these identities to take very messy expressions and turn them into something more manageable. Okay, so we'll get some practice with that during the semester, don't worry. Yeah. Now we're not nobody's going to ask you to memorize these, but there's a lot of these formulas. There is one of the tables I created for this class, as you'll see in the back, is actually a list of some of these. Now here we have the so-called Pythagorean identities, and These are a consequence of the Pythagorean theorem, which, as you remember, simply says, now this is something that nobody forgets. And it turns out that because of this, there are three useful relationships that sometimes will help us reduce the complexity of our expressions when we're dealing with trig functions. Among them being, okay, and then there's two others that fall into place. One plus tangent is secant, and then one plus cotangent squared is the cosecant squared. Okay. Um, well, it turns out the second and the third statements are derived directly from the first one. So really the only one that's completely unique is the first one. Sine squared theta plus cosine squared theta equals 1. It's possible that somebody asked you to memorize this. There's also identities with respect to the sine and the cosine that we need to look at in a second. And you can see them right here. And again, I don't think anyone really expects you to memorize these. All this is really showing us is that some of these trig functions are odd and some are even. Oh God, look at them all. These you should remember, the reciprocal ones. The cosecant is the inverse of the sine. The secant is the inverse of the cosine. The cotangent is the inverse of the tangent. These other ones, I don't know. Um, I don't know if it's worth your while to memorize these, but they may show up though when we're doing problems with trig. Oh, let's see. Oh, that reminds me. What I wanted you to see is that while you have a calculator to help you with this, the problem with the calculator is that if you have, let's say, a trig function, let's say the result is radical 3 over 2, the calculator is not going to show you radical 3 over 2. It'll give you the decimal equivalent of it. So I have found this wonderful little chart for you. Let me go find Brightspace, and I'll show you what I'm referring to. If you look on the tables, it's called trig circle. And, this is not meant to be like a replacement for doing these problems, but it's a way of quickly checking your results. And you'll see that what they've done is they've got all these different angles where they show you both degrees and radians. And in the ordered pair, here's the important thing. Well, yes, these are the XY coordinates. It turns out this is the cosine of this angle, and this is the sine, and that's true for all of them. So if I quickly needed to look up the cosine of 135 degrees, it's negative radical 2 over 2. You can just look it up directly on here. Or 3 pi over 2 radians. Um, there it is. It's 0 and 1. So that's why this chart can be very, very helpful. You might want to have it with you when you're doing assignments or exams, because like I said, if you put this in your calculator, radical 3 over 2, it's not going to pop out of that calculator. It'll give you the decimal equivalent of radical 3 over 2. So this kind of thing can be very helpful. Let's see now. Now, here's something else that might be worth your while keeping track of this somewhere. Another helpful little table, which I just realized I neglected to make my own copy of this thing, but I can take care of that right now. These are the signs for the trig functions in the different quadrants. Okay, so like let's say, for example, I want to look up the cosine of, oh, I don't know, 135. So if you notice, if you look at all the ordered pairs in the second quadrant, um, they're all negative. Okay, so this is helping you keep track of the signs that you'll expect to see in the different quadrants. Okay, reference angles. The reference angle in a nutshell is this. Here's what happens. Uh, I can't think of a good application of this off the top of my head, but what you're really doing is looking for this. Let's say that this is positive 150. The reference angle think it is the closest path back to the horizontal axis, meaning here in this case, it would be this little piece, which is 30 degrees. So this is positive 300 degrees. To get back to the horizontal axis, the quickest way possible, you'd have 60 degrees here, and that is your reference angle. Okay. So you should be able to tell just by looking at the graph what you're trying to do. Now, there are rules you can follow, but I think it's easiest to just look at the graph and see what direction you're heading in. And so, see you can see why this could have been handy in a time when there were no calculators. What they're basically saying is that if you're thinking in terms of radians, which you can do, this works with radians too. Oh, I just realized I'm on a different document here. Hold on. Oops. Let me just quickly take care of this. Yeah, I didn't realize I was on a different page there. So we'll get this on. And this part as well. That way nothing gets lost. Uh-oh. All right, I guess I did something wrong. Hold on one second, I'll get it. All right, I know what I better do. It's really being a pain. So here's what I'll do. I'll grab the whole thing all at once because that's clearly what it wants me to do. All right, that should do it. All right, we're back. So yeah, so imagine you're looking for the sine of 3/4 pi, and looking at the unit circle or the trig circle, that would be right here. And the second term is the sine. And so what is that number? Well, they're saying that the reference angle for 3/4 pi would be 1/4 pi because you would need to move down here in this direction. And by adding one more pi, 1/4 pi, you'd be right back at the horizontal axis. So what this implies is that the sine of 3 pi over 4 is the same thing as the sine of pi over 4, which is radical 2 over 2. Okay. So what this means is that in principle, you really only need to know the trig values in the first quadrant because the rest you can calculate directly from their reference angles. Of course, now we have high-powered calculators, so it's not such a big deal. But at the time this idea was thought of, it was very important. Okay. So yeah, here, what are they doing? They're basically saying that if you were to, it says what is theta? What's the angle for sine theta equals negative radical 3 over 2? And again, we have this wonderful circled trig circle chart that we can look at. Negative radical 3 over 2 would be this one. And its reference angle, which means, where are we? So yeah, 4 pi over 3 reference angle. Yeah, so you end up with pi over 3. So I don't know. That just seems like a very awkward way of going about this. What you can do instead, since you have your calculators anyway, is what you could do is say, well, listen, um, I want to know the values theta when the sine of theta is negative radical 3 over 2. Now, you might remember from your travels that what you could do is solve what's called the arc sine of negative radical 3 over 2. On this calculator, that would be this. So if you happen to have it right in front of you, um, but no, don't forget you have to enter negative radical 3 over 2. It's going to end up being a decimal. And yeah, see, there's the problem. And when it comes back with the angle, it's um it's like a fraction. It's a messy fraction. So but it will work. You will get the right answer. So what they're looking for is pi over 3. And you also have to make sure that you're in the radians mode. So when this stuff pops up again in the new material, we'll go through this very carefully and show you how to find all this information on your calculator. Right now, just be aware that these functions do exist, um, but you must be in the right mode if that's what you're looking for. Okay. So we will discuss this again at great length in a later chapter. Right now, it's enough just to see that this is how you would go about it. Now, they're discussing briefly graphs. We started to look at this ourselves. If you look at this very carefully, you'll see that they have a very unique uh, graph, each of these basic functions. So the sine and the cosine, they both look like roller coasters. The difference is where do they cross the horizontal axis? The sine crosses at 0, the cosine crosses at 1. The tangents have this very strange shape, and they have all of these asymptotes. Why is that? Because remember, if this sine over the cosine is the tangent, well, that means that any angle that has a 0 cosine will result in division by 0. So therefore, the tangent will have an asymptote at any angle whose cosine equals 0. And that's why it looks like that. Okay. All right, then. What else do we have? By the way, if you want to see some weird graphs, look at these. The first one is the cosecant. Same thing, because these are ratios, there are going to be all these different asymptotes. The cosecant is the inverse of the sine. So anywhere the sine is 0, you're going to have an asymptote for the cosecant. The middle one is the secant, same thing. It's 1 over the cosine. Any angle whose cosine is 0 will produce an asymptote on this graph. And then the cotangent is the inverse of the tangent, same thing. This means that anywhere the sine is 0, you're going to have an asymptote. All right. I think that will take care of that. So you know what? I think that's enough reviewing. I think that that was the end of P4. So I think what we'll do is the next time we meet, we'll finally get to start the new content, which is in chapter in this book. That would be chapter 1. Okay. Well, what do you know? Chapter one, where we're going to introduce one of the more important concepts in calculus, which is called the limit. All right, so this is where it starts to get really deep, very deep. Okay, so and they're going to have a bit of reviewing of their own, um, besides what we just got through doing. And so when the time we're done here, we'll be in pretty good shape as far as understanding the new material. But what we're building up to is this notion of limits, which in turn will build us up to the concept of derivatives, which is really the most important thing that you'll do in Calc 1. Okay? So I'll see you all next time.